Alright, student of the course 3035. And I found this problem in an old book. I think this is version 13 of Hibbeler. And the problem is number 5. And now that we are talking about how to take moments and things like that, this brings a very good and very interesting problem of pretty much every day. You see these kind of things happening in front of your eyes. So it would be a great opportunity to study how this work. Like for example, this problem asks to draw a free body diagram of the dumpster D. This is the guy, and that has a mass of about 2.5 megagrams. This has to be converted to a force in Newton and a center of gravity right here at G. And it is supported by a pin at A right here, and a pin connected to the hydraulic cylinder BC short link here. There's a pin here, and there's also a pin here. Display the significance of each force on the diagram, but here I add this determine the force by the hydraulic jack, in this case BC, to as shown here. Now let's start here. Let's draw the main beam. The main beam here is actually this guy here. I have a main beam there, and that being, so that we make sense of out of all our calculation, let's say that our y will go that way and our x is that way. Okay, so with that said, I'm saying is that there's a force here, but also there's a force here on that pin, and that will be FAX and FAY. And now that's pin A. What's going to happen here on B? That's very interesting, because on B there's a force going that way, and that force is at an angle with respect to my y and x, and that's the hydraulic jack, but according to this diagram here is at 30 degrees right here. That's 30 degrees. Now what we need to be is ensure that you understand that you have to try to get that this force, let's call that FH. You have to trying to get the components of FH in a vertical, in this case on the y direction, and but also on the x direction. So you want to try to get, but most important, I would say, just on the perpendicular direction of this bar. That means on the y direction, and that will do, because I will not care much about the one that is going to be decomposed on the x, because it will not have an arm, and you will see that in a second. So that basically give us an idea of what's happening in the bar. Now the question is, what's happening with the G here? Well, on the G, let's draw that somewhere here, another vertical line against this one, and let's say that that G is somewhere here, and that G then is acting down as always, gravity. But there's an issue here, and the issue is that that G will have a component in this direction, but it will also have a component parallel to this line on that direction. So it is actually both components then will have something to say about the moment here at point A, because there's a distance here that says 1.5, and that will create an arm in the moment of A when you do calculation at the moment of A. Now what we need to do is we need to break the force G in two components, the one that is perpendicular here, but we also need the force, the G component, that is parallel to this line as well here. So we need those two, but we also need the hydraulic force, but we want that to be perpendicular to this line, so we want that too as well. So those are basically my three variables that need to be defined, because when you define those three variables, then you can easily take the moment at A as follow. The moment at point A, let's say positive in that direction, equals 0, equal. Now there's a perpendicular force, we call that FG perpendicular, that has to be multiplied by the arm, and the arm in this case is about a distance that I put here, about 3. So that multiply by that distance that is going from here to here, that's 3. Then that's, now we check the sign, that's going in favor of what I said, that this is going to be positive. So that's FGT times 3. Now let's talk about this guy here. This guy, I know that is going the other direction. So in other words, FG parallel to this bar is going that way. That means that I need to multiply by this distance of 1.5. Likewise, how about the hydraulic? The hydraulic is also going on the as in the negative, so that would be minus F hydraulic perpendicular multiplied by the full arm, and the full arm here is 3 plus 1, that would be 4. So the total distance from here to here is about 4, so that's 4. So the only thing that you need to do then is solve for the force, and this force hydraulic perpendicular eventually is going to come from here, which is based on the force on the actual FH. All right, so that's where we are, and that's what we need to work on the angles now. Let's redo the bar here so we start to understand what we're doing. That's the bar, and here is the bottom bar, and this is, according to this information, is 20 degrees. And now we have a force here like this that is hitting the 30 degrees, but then I said that we need to work on the perpendicular line of that, and what we need to know is what is this here, what is this, that the degree here. So let's work on the vertical here, like the vertical as well, because the vertical, whoops, that vertical didn't work that well, because the vertical is easy, because you know that that's 90, and that makes life easier. So that's, this here is 70. Now here's the story between this guy and this guy, between this guy and this guy, they are perpendicular, and that's nice, because then you know that this is actually this is 20, so you got a 20 here. Now the question is, what is this? And that's the big deal, because when you break that angle, you can break this into this perpendicular line. So what is that? Well, that is, you got 30 here, but you also got 90 here. So the whole thing from here to here, guess what? 60. That's it. 60 degree, because that's 30, 90, 60 plus 30 is 90, so 90 plus 90, 180. So you got the big triangle, you got the 180, no problem there. So now if that's 60, you subtract the 20, that's 40. So the big deal here is that question mark is 40. So this is what you got. You got, again, let's draw this again. You got that there, and now you got the hydraulic force going like this, but the line that is perpendicular here is 40 degrees, and that's the only thing that you care, the 40 degrees, because when you do that, the force, or the hydraulic force, the force hydraulic, which is perpendicular to the bar, is going to be then FH times, in this case, the cosines of 40. And that's it. So then you got the first one. This, you break on this. The second one, you don't care. I'm gonna write it down, but you don't care on that one, because the one that right on the bar here, there's no arm on that line. there's no arm, so I'm gonna write it anyway. So that's gonna be FH time, in this case, so it's sort of like a force here coming parallel. This one, you can get it, so you know that it's gonna be a sine of 40 degrees. But you don't care about that one. It's only the component that is perpendicular to the bar. Again, this is point A. Now, how about what's going on with G? Well, G, I kind of let you know what's going on with here. So let me rework that a little bit on G. So you have this bar that is go like this, and there's a G somewhere here. Actually, I like to draw first what is important, this force here, and G is here. That would do. And we also know that this goes like this, and that this is 20 degrees, and gravity will always do this kind of trick down, and that helped a lot, because what's going to happen is that you also, this force is going to be down. I can rewrite a triangle here as well. So what is happening here is happening here. So this is 20 degrees as well. This line and this line are parallel. This is 90. So you got 70 here. And guess what? This line and this line are 90 degrees. So you know that this guy here is 20 degrees. And that's the important thing. Because then you know that this force here is called FG. So what you have to do is that, for example, FG perpendicular to the bar is going to be breaking this guy into this. So this is 20. So that would be FG times, in this case, cosine of 20. Now, the other one is important as well. So you want this component as well. So that's FG, in this case parallel to the bar. It's going to be FG times sine of 20, and that will do. So we got everything that we need. We have, all the forces are required. And let me write here the FHT, just for the sake of the argument. FHT, which is the hydraulic force, equal to the hydraulic force times the cosine of 40 degrees. So I got the three forces. Now let's draw this bar again. And here's the story. I have a point here. I have a vertical line here, but I also have something coming down here. So this is what I call this is called FG parallel, and this is what I call FG perpendicular. And now I also have the other force, which is FHT, this guy here, which is perpendicular. That's going to call FH, in this case perpendicular. That will do. So, and this is point A. With that said, I can take the moment here. Remember that here also, as part of the free diagram, you also have this, like for example FAY, but you also have, let me draw this a little bit better. You also have FAX, because you coordinate R, Y, and X to make life easier. So what we're going to do is now take the moment at A. These two guys doesn't have an arm, so they move out, they die. So we have the moment at A, and let's take, for the sake of the argument, positive in that direction. So that will be 0, and because a pin doesn't hold any moment, so that would be here we go. I'm taking this direction, the positive direction, and this force here, I think it's the only one that goes in the positive direction. So that means that whatever is this distance from here to here, according to my diagram, I think I already did that. It's right here. I can use that as well. So actually, you know what? Let's use this because it's already have it. There we go. And that's where we are. So let's see. Now, so MA positive in that direction equal FGT. Now, one thing that I haven't done is What are these? What is FG? We don't know FG yet already. So let's work on FG and we finish this. FG, according to the book or the problem, is about 2.5 megagrams. 2.5 megagrams. Let's see. 2.5 megagrams. That's about 2.5 times 10 to the 6 grams. So that's not force, that's mass. So I need to multiply that guy by 9.81 to make it Newton. So now 9.81, but there's a problem. I have gram here, so basically what you need to do, let's do a little bit of math here. So 9.81, and I can put the units if you want to. Let's put the units so that we get this straight. 9.81 meter second square, but 1,000 gram is 1 kilogram. Now let's see where we are. Grams cancel with grams, and this is mega, so that's meaning 1 m is 1 times 10 to the 6. That's what it means. So this m cancel with this m, and you end up with Fg equal 2.5 times 9.81 times 1 times 1 times 10 to the 6, and all that divided by 1,000. You pick all the units here, so you end up kilograms meter second square, and all that obviously is a Newton. So Fg for our problem is what it is. I need a calculator here. Hold for a second. 2.5 times 9.81 times 1 exponential to the 6 divided by 1,000. 24,525 Newton. So we got that, and now what happened with the equation? Right here. So with that said, now we can get and solve our problem. In this case, Fg, and we can use here the definition based on that number, this one here. So see if I can get this. So all right, so here we are. So Fg is that one. So basically you multiply that. Let's get this here. So you multiply that by cosine of 20, and you do the same here of 24,525 times the sine of 20, and let's see. This is about 23,045, 046 if I round it up. That would do. How about the other one? The other one is 24 times the sine of 20. 8,388. Oops. 388. And those are newtons. All right, so we got that. Now let's see where we are now. Now we are ready then to apply our equation here and solve eventually for in this case for the hydraulic force, which is the our variable, the main variable here. So let's apply this equation the way it is, and let's see how we gonna end up on this. So let's see, MA, this direction positive equals 0. That means that we need F, the force of G perpendicular. That's 23 046 times 3 minus FG, that is that guy here, 8388 times 1.5 minus FH, the hydraulic. But the hydraulic, this in the perpendicular is going to be FH times cosine of 40. And then FH cosine of 40 multiplied by the arm, which in this case is, we pop this big, is from here to here. That's 3 plus 1, that's 4. Oops, that's 4 here, so times 4. So the result then will be, we resolve for FH, which is basically 23,046 times 3 minus all that divided by, so that's FH is equal cosine of 40, and there's a 4 here, which is the arm, and FH finally is, let's see how this end up being. So that's about 23 046 times 3 minus 83. That's about 56 556 556, and that number divided by 4 and by cosine of 40. So the result is it's about 18,457 Newton, or about 18.5 kilonewton. So that's the answer. So this is the result for the hydraulic force. Now, I haven't looked into more detail about what's going to happen with FAX, FAY, and all the other components of those. We can work it out, because actually there's going to be FH here. It's going to have another force coming down, and a force what is perpendicular to the bar here. Oops, sorry for this. I'm not sure. I had the keyboard connected and it's creating a mess. So basically we can work out the forces that are either tangential to this line or normal to this line, which I call here Y and X, and work out the details about what are these particular value here, because basically now that you have HS, and you have also an idea of what this guy is as well, the force coming down and the force coming in this direction, then you can work out the details about the unknowns here. So let's do that, and let's wrap up this video. So to do that, let's now work some of these details back again. Let's see, I should work it here because it's easier now that we have the magnitude of each force, and let's work in this direction. Like for example, forces that are normal will have to deal with this guy here. So like for example, let's see if I can get this better. The sum, let's see if let me disconnect the keyboard so it doesn't create a problem here. In order to get and to solve for Fix and Foy, which is this actually is the normal force on the bar, and this is in the direction of the tangent, or in the X direction as shown here. So what we need to do is to get the bar again. Let's draw the bar, and let's get all those forces. Like for example, I have a force here which is FH normal. I can write normal or vertical, perpendicular, sorry, to the bar here. But I also have another force that is coming down here, and that force is tangential to, or parallel to the x-axis. Now we have those. Now I have another force coming here, which is like this, acting on the perpendicular. That's force G perpendicular, but I also have another force coming this direction, which is FG. It's going to be FG parallel, but then I have another force here, which is obviously this force here, which is FAY, which is normal to the bar, but I also have one that is tangential to the bar. That's going to be FAX. I think that I have all the forces. These two guys here on the pin, no moment because it's a pin, and I have these two forces due to the dumb weight, which is about the force that is perpendicular to the bar and the one that is tangential to the bar, and I have here again the hydraulic force of the jack, which is perpendicular, and the one that is tangential. I know these forces already, all of them, so it's easy to solve for these guys, and we'll do the following. We're going to do that the sum of all forces, for example, on the normal to the bar, that will be on the y direction, and the force on the y direction will be 0, and we assume positive up. You remember, like this, yx is positive toward those directions. So that means that here we have, if we are talking about the y, so that's going to be f a y, that's positive, going up, minus whatever is coming down, which is going to be f g perpendicular to the bar, but then plus f h perpendicular to the bar equals 0. So f a y equal f g perpendicular. Let me get this the sign better. So I'm moving this back and this as well. So you get f g perpendicular minus f h perpendicular, and that will do. So we get the numbers like fg perpendicular. If I got that, fg perpendicular is 23,046. So 23,046 minus the hydraulic force that is perpendicular, and that hydraulic force perpendicular had to be calculated because that's coming from here. So let's calculate that from here. So FH eventually, that number, let me shrink this, is about 18.5 kilonewton. So I'm gonna use that. 18,500 Newton multiplied by the cosine of 40, and that will be 18,500 Newton times the cosines of 40. That's 14,171 Newton, 72 actually, and that will do. So 14,172. So we go back here, minus 14,171, and FAY is equal and that will be about 8,874 Newton. and or FAY equal 8.9 kilonewton, one decimal place. So meaning that the force of the pin is going up in that direction. And now how about FAX? FAX is the same thing. We do the sum of all forces on the x direction according to this diagram, and we said positive, let's say positive on that direction equal, then FAX is positive, but then this force is on the negative, so minus is going to be FG, which is parallel to the bar, minus F, the hydraulic jack, that is also parallel, meaning that the force on the X will be FG parallel plus FH parallel as well. So F, the force in X direction, FG parallel is 8388 plus FH, which is parallel as well. We haven't calculated that, but then that has to be calculated from, and we're going to calculate here. FH, which is parallel or not, or tangential to the bar, is going to be the value of the 18500. Be careful here, times. Now we are talking about this force here, the one coming down on the bar. So that means it's a sine of 40. It's this side, sine of 40. So the only thing that I need to check on this is instead of cosine of 40, is sine of 40, and that will be 18500 times sine of 40. That's about 11A92 Newton. So FAX then will be 11A92, or FAX finally is about 20,280 Newton, or about 20.3 kilonewton, just to say the least. All right, so now I have, let's throw the bar here to get this done. So this is the point. I have a force here and a force here, and the actual force, the magnitude of that force actually is going up, not in that direction, but up, because this guy is about 8.9 kilonewton, and this one here is about 20.3 kilonewton. So the magnitude, the total force on the pin A, the magnitude will be the square root of 20.3 square plus 8.9 square, and that force is, let's see, so we have the square root of 491.3 equal 22.16, about 22.2. All right, so we got the 22.2 kilonewton here, but you know how I draw this may be misleading, because basically I need to calculate that angle based on these two forces, and for that just use the old tangent of theta, right, is equal to whatever on the y direction, in this case on 8.9 divided by 20.3. So theta is equal the inverse of the tangent 8.9 divided by 20.3, and that theta will be, let's see, that's 8 inverse shift here, tangent of 8.9 divided by 20.3, and that's about 23 degrees, meaning that that actual force is somewhere from the x direction, is coming like that. So here I have about 23.7 degrees. Actually, we're gonna write it here, 23.7 degrees. So that's here, 23.7 degrees. So this is the angle of that force going up. So that force actually that's where the angle is working toward that direction. All right, so that kind of finished the whole thing. Now that we were able to get everything, according to and more, because here only they ask for the free diagram, but I add this part here, and also I add how to calculate those forces, particularly the one happening right. Oops, there's something here kind of got deleted, but you got the idea. Particularly these forces here, which is also part of the free body diagram. More than enough. Thank you for watching. Bye.